The title of our webinar is called Process Capability and Statistical Process Control with SigmaXL. The agenda, we're going to cover a process capability, capability combination report, process capability for non-normal data, and then we'll go into control charts, individuals control charts, X-bar and R control charts, and then, time permitting, we'll show some of the new features in SigmaXL version 6 pertaining to control charts. I wanted to point out that on the topic of process capability in SigmaXL, under templates and calculators, we have arranged the templates and calculators into groups. So you have your DMAIC and DFSS templates, your lean templates, and so forth. And here, under basic process capability templates, there are 4 templates that are available. The Sigma level for discrete data, pass-fail data, the Sigma level for continuous data, so continuous data like cycle time, process capability, and then process capability and confidence intervals. So I'm just going to pull up the process capability, and this is a very straightforward template that allows you to plug in the mean, the standard deviation, the upper and lower spec limit, and you get your process capability indices. Now I'll take this time to talk about the difference between CP and PP. CP is the short-term process capability, and PP is the long-term or overall process capability. And PP refers to process performance. CP really refers to a potential process capability. If the process is stable, then the CP and the PP should be the same. This is discussed in the workbook, and you're welcome to refer to the workbook. Much of what we're going to cover in this webinar comes straight out of the workbook, so you can come back to that later for future reference. I wanted to comment on whatever you put in terms of the mean and the standard dev. If you're putting in long-term data, then these indices are the overall, the PP, the PPK. If you're putting in short-term numbers, then you're getting the CP and the CPK. All right? So that's just the process capability indices. We also have a more sophisticated process capability template that includes confidence interval. There's a lot more information here. Again, this is still assuming that the data are normally distributed. This is for continuous data, so cycle time, something where, for example, a day and a half has meaning, so the data is on a continuum. And so you're getting your expected defects per million above the upper spec limit, the expected defects per million below the lower spec limit, the overall defects per million, and then we also give the overall yield, which is the percentage of good stuff. And then the CP and the PP calculations are all given on the right-hand side. In addition, you have the confidence intervals, so you have the margin of error on your CP. As you can see here, this is quite a range. If you're looking at PPK, 0.46 to 0.87, or the CP value, 0.74 to 1.26. That's quite a range of values, and the reason that you're seeing a wide range is because of the small sample size of 30. So as a rule of thumb, 30 is the minimum for process capability. 50 is certainly better than 30, but if you can afford it, use 100 observations to compute your process capability indices. So those are the templates pertaining to process capability. We also have some control chart templates, which I'll just highlight here. Under templates and calculators, we have basic control chart templates, individuals chart, and a C chart. So these are just for a quick and easy creation of control charts. I'll just pull up the individuals chart. You can type in some data, and I'll just put in some dummy numbers, and then maybe one large number. and then create your individual's control chart. And there's your quick and easy control chart. Okay, so that's the template, and then we have one for C chart if you're actually using count data. So individuals chart for data that's like cycle time. The C chart is based on the Poisson distribution, and that's for count data, counting defects. So we'll now proceed to the capability combination report, delivery times data, and go back to sheet 1. So what I have here is a hotel breakfast room service delivery. If the order arrived on time, we captured that the deviation would be 0. If the order was late, it's a positive deviation. And if the order is early, it's a negative. So the negative denotes breakfast that was delivered actually before it was requested or before the target time. Now, the specification limits that we're going to use are plus and minus 10. If the breakfast is more than 10 minutes late, then you're running late for your meeting. If breakfast is delivered more than 10 minutes early, then you're still in the shower and you're not able to get to the door. So in either case, it's a defect more than 10 minutes late or less than or earlier than 10 minutes. Either case, it's considered a delivery defect. So that's what we're going to use, plus 10 for the upper spec limit and minus 10 for the lower spec limit. So we'll go ahead and we'll do a process capability study on this. Under process capability, we have, here are the templates again that I showed you earlier under templates and calculators. I'm just going to go to histograms and process capability. So we'll start with the simplest tool and then kind of build up. There are quite a few observations here, 726 observations. So I plug in the delivery time deviation. And as I said, the upper spec limit was 10, the target is 0, and the lower spec limit is minus 10. This is minutes. And if I click OK, I can visually see these are the late deliveries. Everything to the right of the upper spec limit are the late deliveries. Everything to the left of the lower spec limit are the early deliveries. Now our report, our capability report, shows the expected performance. This is based on normal distribution theory, and the actual performance. So the actual is just simply a count of percentage above the upper spec limit, percentage below the lower spec limit, and then the percentage total out of spec. Now, one of the things that we should have done prior to running the process capability was to assess whether or not the data was normally distributed. We could do that running a normal probability plot, but I'm going to run the capability combination report because in the capability combination report, you actually get the test for normality as well as the process capability indices. Now, just before we proceed here, we have PP and we have PPK. The rule of thumb, of course, less than 1 is bad. Greater than 1.33 is good. Greater than 1.5 is excellent, and greater than 2 is world class. So less than 1 is bad. 1.5 and higher is excellent, and 2 and higher is world class. 6 Sigma quality would correspond to a PP of 2 and a PPK of 1.5. Now, CPM we're not going to get into. That's an index that pertains to, it incorporates a penalty for deviation from target. But if you have a difference between PP and PPK, that's a centering issue. And as you can see, we're off center here. On average, we're 6 minutes late. Bottom line on this is that we have a lousy process. And I like to remind people that, okay, there's a wealth of statistics being presented here, but you can always just look at the graph. Look at the histogram and how does the process look. And obviously, we have work to do. In this particular case, there's a lot of variation, and the average is off of the target. So they'd have to work on ways to reduce the variation and to center the process. Now, this is the basic process capability. Now I'm going to switch over and go back to the data and run the capability combination report. So back to process capability combination report. This is for individual observations and delivery time deviation. There's additional options that pertain to the control chart. I'm not going to change anything there, but we'll put our upper spec limit of 10, our target of 0, and our lower spec limit of -10. Okay, so the test for special causes are also turned on. And we run that. This will take a little bit of time. There are 720 observations, a lot of calculations going on. And this report, okay, so the histogram is what we saw earlier. Now notice the normal probability plot. The normal prob plot is approximately a straight line. There is, some stuff going on in the tails. But if we look at the Anderson-Darling test, a p-value of 0.06 indicates that the data can be considered to be normal. 0.05 is the cut point. Less than 0.05, we would say the data is not normal. So it's just basically just squeaks by our normality test. And we're not proving the data to be non-normal, but we don't have enough evidence to call this data not normal. So we'll consider it to be normally distributed. The statistics that we saw earlier, the percentage above the upper spec limit, below the lower spec limit, this is the expected based on normal distribution theory, and this is the actual percentage observed above and below the lower spec limit. We do have our PP and our CPK. PP and CP are quite close, so there's really not an issue with stability. It's still a lousy process, but it's a stable process. So that's the thing. Just because you have a stable process doesn't mean it's a good process. And PPK versus CPK, not much of a difference, and so stability is really not an issue here. Centering is an issue. And when you look at the individual's control chart, there are some tests for special causes triggering. Nothing is exceeding the upper or lower control limit. We are seeing some small disturbances, so there may be some signals there. One of the problems with looking at historical data, looking at, say, a year's worth of data, it's very difficult to go back and identify what happened at a particular point in time with these tests for special causes. And so what we recommend is that the test for special causes be used in real time. So as new data is coming in, you have the test for special causes turned on, and then if you get a signal, then you are able in real time to take corrective action. So it improves the sensitivity of your control chart. There's also a moving range chart shown here as well, and you are getting some signals on the moving range chart. So it's not a perfectly stable process, but it is, it could be worse. So the thing is that as a result, what we're looking at here is fundamentally this is a process that has excessive variation. We need to reduce that variation, and we also need to center the process. So that's the capability, process capability combination report. And what I want to look at now is data that is not normal and run the process capability on non-normal data. And this is, again, in the workbook. So we have non-normal cycle time. With my non-normal cycle time, let me begin with just let me do under graphical tools, a normal probability plot, just so we can see what that looks like. If I do a normal probability plot, you can clearly see that this data does not fall in a straight line. It's not normal. If I do a histogram graphical tool, let me just run a histogram in descriptive statistics. And if I run histogram and descriptive statistics, we clearly see with the Anderson-Darling test, the p-value is very low, and so this is data that is not normally distributed. Now, just before we proceed with dealing with this non-normal data, a comment: if the data is not normal because you have an outlier, a single outlier, then it is not appropriate to use these advanced tools. Find out why you have that outlier, deal with the root cause, and proceed from there. Similarly, if you have some X factor, something changed in the process, a bimodal distribution, it's inappropriate to apply techniques like transformation and distribution fitting to data that has a bimodal distribution. You need to find out what your X factor is, resolve that, and then proceed from there. So I want to preface what we're about to do with just good practice, that we don't want to just torture the data until it confesses. We want to go in with understanding. There is also controversy around how do you deal with non-normal data. Some practitioners, like Donald Wheeler, say don't do anything, just go ahead and plot your control charts, your individuals charts with the non-normal data, and take action from there. I am of the camp where it is an issue, and you will get false alarms and misses if you try to treat non-normal data as though it were normal. And to illustrate that, let's go back and let's say that we went ahead and we just treated this data as if it were normal. Let's see what happens. I'm going to run a process capability study. So process capability, and I'll do capability combination report individuals because that gives me a control chart as well. And go ahead and I'll put the cycle time in. The upper spec limit in this case is 1,000 minutes, and we'll just run that. So as we saw earlier, the data is not normally distributed. There's also quite a large difference between expected performance of 40% and actual performance of 10%. So this is quite large. Remember, expected is based on normal distribution theory. And the Anderson-Darling normality test, again, as we saw earlier, tells you that this low p-value says that the data is not normally distributed. The control chart looks like the process is out of control. Okay? So keep that in mind now. What appears to be an unstable process, one might just say, well, just find out why you have these 2 points and address them. But there's a lot of situations, cycle time is one, where the data is just inherently not normal. And they're not necessarily assignable causes that are tied to some of the points that are further out. They are actually a part of the natural variation of the process. Now, this is where process knowledge comes in. You have to kind of also be a good judge, in terms of, is this something that's behaving naturally and we just have to model it properly, or are we actually dealing with outliers? The prob plot can help you. If the prob plot shows the bulk of the data falling in a straight line, and then maybe 1 point far away, then you could argue that that could be an outlier. Keep in mind also we only have 30 data points here. It's helpful to have a larger sample size, and then it becomes even clearer whether you're dealing with outliers or whether you're dealing with something that is inherently not normal. So with that, we're now going to deal with this as non-normal data. And so in SigmaXL, We go into process capability. This is a new feature in version 6. In an earlier webinar, I demonstrated this. I'm just going to focus in on the capability combination report for non-normal data. And then we'll click Next. And we'll go ahead and run that. Now, one of the most commonly used tools to deal with non-normal data is the Box-Cox transformation, which raises basically finds a power transformation, a suitable power transformation to convert the data to normal distribution. Sometimes, however, Box-Cox doesn't work, and so you might want to use a more powerful transformation called the Johnson transformation. There are also a number of different distributions that are permitted, and log normal, exponential, Weibull, beta, gamma, logistic, log logistic, largest and smallest extreme values, so there's quite a few choices here. And for most practitioners, it would be a very difficult choice selecting a particular distribution. So what we have is this automatic best fit, and it will go through and find the best possible fit. Let's start with the Box-Cox transformation, and I'll put in the upper specification limit, again, of 1,000, and we'll go ahead and run that. Now, this shows you the fit based on the Box-Cox, and the probability plot shows you that you have pretty close to a straight line, and the report, and let me scroll over, we can look at the Anderson-Darling. After transformation, this p-value of 0.4 indicates that the transformed data is now normally distributed, but the original data was not normally distributed. Notice that, okay, it's still a lousy process, but our expected overall performance is much closer to our actual performance. So obviously still a process in need of improvement, but what we have here is a more reliable indicator. Now, if I look at the control chart, notice that everything's in control. And so after transforming the data, and there was a logarithmic transformation that was used, and we create the control chart, what we see is that in actual fact it's a stable process. The first chart is the raw data with percentile control limits. The second chart is the transformed data, so it's an individual's chart on the transformed data, and this is the moving range chart on the transformed data. And you can apply the test for special causes on the transformed data. So again, a lot of information here, but when appropriate, we recommend that that this non-normal data, we use the right tools to get the right results. Now, one other thing I wanted to come back to is under process capability report, or sorry, non-normal distribution fitting, we also have in the distribution fitting, it will go through and it will actually give you a report of all the different transformations and distributions. So you can actually look and see what sigma, all the various transformations and distributions and what they look like. Actually, I'll run that. Now, once it's done, it sorts it from best fit, and what's nice here is that, as you can see now, the best fit is the log logistic. If I scroll over, I can see that that's definitely a good fit, and we use the p-value as the basis for determining. We actually do an estimate of the p-value and rank sort based on Anderson-Darling p-value. So what I want to do is just simply scroll through so that you can see, starting with the log logistic, followed by, this is now the 3-parameter log logistic. There's the box Cox transformation, log normal. That's 2-parameter, 3-parameter. And so amongst the first group, probably you could have picked any one of those. But as you progress, and there's the Johnson, as you progress, things get worse. And you can start to see the line deviating from a straight line. So as you scroll down, the distributions are getting worse and worse. Okay? So this is a nice tool to help you decide which distribution you want to work with. However, if you have no idea, then there's one other tool I'll show you, and then we'll move on to control charts. That is, under process capability, I'll run the non-normal capability combination report. Again, now upper spec limit of 1,000. Plug in my cycle time. This time I'm going to run automatic best fit, and we'll go ahead and run that. It's going through and it's testing out the box Cox transformation. It's testing out the Johnson transformation. It's going through all of the various possible distributions. Here we go. The log logistic 2-parameter is the selected distribution, and there are so a little bit different from the box Cox. Not a lot different, but it's considered to be the best possible. Now, on the other hand, one might argue, well, for presenting to management, it's going to be a little more difficult to talk about a log logistic, whereas a logarithmic transformation is much more intuitive. And so, you might be better off staying with that logarithmic transformation that was provided by box Cox and going ahead and using that. Keep in mind, we only have 30 observations in this data set, so there's going to be, what we consider to be the best is the best calculated with those 30 data points. Maybe if we had 100 data points, there might, it might have selected something slightly different. So it's not a big deal if you pick second best or third best. However, when you get way down to the bottom, you see those distributions that are really lousy fits, you're trying to fit a square peg in a round hole, then you definitely don't want to be selecting any of those distributions over here at the, down here at the bottom of the distribution fitting report. So basically, regular smallest extreme value, that would be definitely a bad fit. Okay. I wanted to mention in process capability, and it's grayed out if I go to specify distribution, I have a choice between what is called the z-score method and the percentile method. And what this is the z-score method is based on the process capability using the transform data, whereas the percentile method, it uses the 0.135 and the 99.865 percentiles. Andy Sleeper, in his book Six Sigma Distribution Modeling, presents a very strong case for using the z-score method, and this is the method that we have in as the default method. However, a lot of software defaults to the ISO method, and that's why we have that alternate capability index method for non-normal data. But we do recommend the z-score method be used. So let me begin under control charts. What we have is a control chart selection tool. This is really nice for getting people started on control charts, and it follows the flow chart that you find in most training materials, where you select between continuous data and discrete data. If you have continuous data, are you dealing with individuals or subgroups? If you're dealing with subgroups, are you going to use an X bar and R chart or an X bar and S chart? Well, that depends on what sample size you have. Now, of course, you can have an X bar and S chart with a smaller sample size, but what we wanted to do was to provide, kind of the typical flow chart, a selection of tools. If you are dealing with individuals, you can plot the individuals chart or the individuals in moving range. If you're dealing with discrete data, do you have defectives? That's pass-fail type data. Or are you looking at defects, more than one defect per unit? If you're dealing with defectives, do you have a constant sample size or subgroup size? If so, use a P-chart or an NP chart. P-chart is proportion defective, NP chart is number of defectives. If you're looking at defects, then, and the sample size is constant, you can use the C-chart or the U-chart. The C-chart is the count of defects, the U-chart is the count of defects per unit. If the subgroup size varies, then you're locked into the U-chart. Okay, so this is a helpful tool. There is another category here, which is the subgroup sample size is very large and assumptions are not met. David Laney, in quality engineering, published a paper on P-primed and U-primed, and these, basically what it is, it's a hybrid between a P-chart and an individuals chart. When you have very large sample sizes, it's often that the assumption of a binomial or a Poisson distribution is not valid, and what you end up with is over-dispersion, and you end up with just lots of false alarms. And some practitioners just say, okay, if your sample size is large, just take the percentages and treat that as individuals on an individuals chart. The problem with that is then you lose information that is within the sample size. So the P-prime chart is a nice hybrid, and think of it exactly as that, as a hybrid between the P-chart and the individuals chart. And the U-prime chart is a hybrid between the U-chart and the individuals chart. All right, so with that, I'm actually just going to start with an individuals chart. And we'll run the individuals chart of delivery time deviation. I can turn on my test for special causes. I have Sigma zone lines. That's a new feature in version 6. There are advanced options that I can get a process capability report. I'm not going to do that here. We've already run the process capability. Later on, I'll show you how you can split your limits. Okay, so let me just go ahead and run this now. We'll create the individual. And here we go. Again, lots of data here, over 720 observations. Our test for special cause report is nice because it's tells you that 30 observations have failed the test, and you can go down row by row and then scoot across and see which tests had failed. But keep in mind my caution that I mentioned earlier, which is when you have your test for special causes on and you're looking at long-term historical data, it's going to be really difficult to go back and figure out what were the assignable causes. The real practical application for test for special causes is in a real-time situation where you have fresh data coming in and you have a sensitive chart so that you're able to determine right then and there what the assignable causes are, what the special causes are. Keep in mind also that when you turn all the tests on, your false alarm rate goes up quite substantially. It's a 4-fold increase in false alarm rate when you turn all the tests on. So instead of getting one false alarm in 370 observations, it's one false alarm in less than 100. So that's just a caution, but the test for special causes do improve your sensitivity. Some of the tools that we have SigmaXL chart tools. We can show last 30 data points, so it'll actually zoom in. I can, and then I'll go back. I should have actually, let me run that again, enable scrolling, and I will continue and click OK. And so now I can scroll through my my control chart. All right, I can freeze the chart. Other tools that we have, if you want, you can actually exclude data points. I'm not going to do that here. Or you can add a comment, add data label, and all right, so it's basically whatever the comment here gets put in as a comment. You can do that in Excel as well by clicking on the individual data point, but it just allows you to add a text comment to a data point. Okay, so that's the chart tools with the zoom on the control chart and the scrolling feature. Let me do a X bar and R chart. We are running short of time here, so I just want to do a few more. Let me do X bar control charts. So what I want to do is just, this data is subgroups across rows, catapult data, where an operator fires a catapult. They're trying to hit a 100-inch target, and so you can see shot 1, shot 2, shot 3. So allow me to create a control chart. I've only selected observations 1 through 20, and that's because the data was collected initially, and then 21 through 25, there was actually a process change, and I want to illustrate that. So I'm going to start with subgroups 1 through 20. I'll just use the X bar and R chart. And we have subgroups across rows, so shot 1 through 3. Subgroups across rows. We can put operator in as our x-axis label. I'll put the test for special causes on, and then we'll just go ahead and run that. And as we can see here, clearly this is a stable process. There are no signals. None of the tests are failing. And so we obviously have a stable catapult process. Not necessarily a good one. Again, you can have excessive variation and it's stable, but still a process that needs to be improved. Stability is not the same as capability. Both are important, but they are different. And what I'm going to do is I'm going to show you the chart tool that shows I can just add the data. Those 5 additional data points can get added to this existing chart. And now we see that, in fact, with the new data, we have an unstable process. Okay, so something has changed. Turns out the rubber band was replaced, so that's the assignable cause. And the corrective action is not to go back and get to the old rubber band, but simply to adjust the pullback angle on the catapult. All right, so that's the X bar and R chart showing you with the ability to add data to an existing chart. One more thing I want to show, and that is, let's say you have a process that you have improved. So I'm going to go to, I have catapult before and after improvement. So in this case, what I want to show is, and this is good for a process improvement project, I'm going to I'm just going to use this as individual observations, but I want to show you how the split limits work. So we'll go into control charts, individuals. So distance is my data variable y. And what I want to do is I want to go to advanced options, and I'm going to specify historical group. I'm going to split by before and after. And so when I do that, what we have is we have obviously much more variation before improvement, and after improvement we have much less variation. In this particular case, variation reduction was the primary focus. If it were customer satisfaction, then you would want to show an increase in the average as well as a reduction in the variation. We'll call that a wrap, and would like to open it up to any questions that anybody might have.